Earth is the only planet in our solar system that burns. And there's one main reason why. Plants. Since they first evolved more than 400 million years ago, land plants have changed the world, from the soil to the atmosphere. Even the origin of fire is tied to the origin of plants. Fire couldn't exist here until the fuel and oxygen from land plants made this planet flammable. So for nearly 500 million years, the Earth has been in flames. In turn, fire shapes the patterns of life, the climate, and ultimately, our own survival. But fire is changing.
That is unreal.
Over the past decade, every forested continent has seen an alarming surge in large, uncontrollable fires. Megafires.
The sort of metaphoric equivalent of an atomic bomb. That's what a megafire is. It's muscular, it's mean, it's big, it's aggressive.
Not only are they increasing in number, but the nature of these fires is also changing.
Really fast burning fires, and their local intensity is just amazing. These are extraordinary fire events.
So extraordinary, they demolish the very ecosystems that have thrived with fire for millennia.
Here in the southwest US, the fires have become so large and so intense that whole forests are transforming into entirely different landscapes.
No longer can we count on what we thought we knew about fire.
In Australia, catastrophic megafires are tearing landscapes apart. It means we all have to rethink how to live on this flammable continent.
What's behind the rise of megafires? What do they mean for life as we know it? In this Catalyst special, we travel to opposite sides of the planet to find out.
It's quiet and still on the eastern side of the Jemez Mountains in the southwest US. The trees here offer little shade.
We're walking through part of the first day of the Las Conchas fire, which had stunning fire behavior the first day. It burned 43,000 acres in the first 14 hours.
Wow, how fast is that?
Almost 1 acre per second. The Las Conchas fire was outside the experience of anybody alive in New Mexico, including me. The scale of that fire was almost quadruple the size of the previous largest fire in the Jemez. It was shocking, actually, to the fire people. They'd never seen this kind of fire behavior. Certainly shocking to ecologists like myself as well.
In that fire, Dr. Craig Allen watched the obliteration of forests he'd been studying for decades.
We're in the middle of a huge patch, about 30,000 acres, where every conifer tree was killed. These trees don't have seed banks either in the soil or in the canopies. They need mother trees to survive, and they've been wiped out over this huge area.
So basically, you've got an ecosystem that's changed overnight.
Literally overnight. You don't get these tree species back on these sites.
The term megafire didn't enter the scientific literature until recently. It refers to a wildfire that's not just large, but extreme in its behaviour, with catastrophic impacts. In the past, fires burnt much less severely, leaving living trees to regenerate the scorched areas. But as you can see behind me, for many thousands of hectares, there's not a single living conifer left. And there won't be for hundreds of years to come. A little further in our trek, and the future landscape is impossible to deny.
So as we look across this open area, this used to be ponderosa pine forest as far as the eye could see. And you can't even see the evidence, hardly, that this was a forest before.
The pine forest that was here was hit by 2 high-severity fires, 15 years apart. The first killed the trees, the second erased even the blackened trunks. So how long has it been ponderosa forest for?
Thousands of years.
And this is the new landscape?
Yep.
Instead of trees, grasses and shrubs have moved in. At lower elevations, there's barely any vegetation at all.
The first night of the Las Conchas fire, an amazing thing happened. There was this huge convection cloud. They create these pyrocumulus clouds from the heat. When the plume collapsed, it just incinerated all the above-ground biomass down in some very dry areas, some of which were very sparsely vegetated. You couldn't even hardly imagine fire could carry through them. And it burned off the organic, rich top portion of the soil, leaving a very desertified landscape afterwards, a moonscape. This hurts a bit, actually, personally. These are forests I've spent more than 30 years studying. Some of the individual trees are friends.
As we head back to Craig's office, I finally get to see what the burnt-out landscape once looked like. A kaleidoscope of green and gold, brimming with wildlife. Here, mountain elk, coyotes and prairie dogs are a regular sight. We're travelling at the edge of New Mexico's Valles Caldera, the collapsed cone of a supervolcano. The changing elevations create these forested sky islands in a sea of grassland. It's a strikingly beautiful place. It's also one of the most intensely studied places in the world when it comes to fire history.
So take a look at this map series here. These are historic maps of fires in the whole Jemez Mountain Range. This goes back 104 years to 1909. So in the first 60 years, you can see there were very few fires and they were small. And this takes us 20 more years to 1989, which was a wet period. The 1980s, there was almost nothing. And then, as we move forward, this blue patterns are the fires from the 90s.
They're getting bigger.
And now it really, as we go 10 more years...
Wow, that's massive compared to the last fire.
This fire was at the time more or less the largest fire in the recorded history of New Mexico. And now if we take it to the present, just 4 more years,
Whoa.
you see that
Jeez.
this huge fire is the Las Conchas fire that we were just in.
When the fire maps are run together, the last few years are truly a standout. But this recent explosion of fire is by no means unique to New Mexico.
We're seeing similar dramatic increases in fire across much of Western North America and in many other parts of the world as well.
This is the Yosemite Rim Fire, California's 3rd largest in nearly a century of records. In their list of the top 10 biggest wildfires, most occurred after the year 2000. Only one on the list was before the 1970s. A study of boreal forests in Alaska has found they're burning at the highest rate in 10,000 years. In 2012, Russia's worst fire year on record, over 30 million hectares of Siberian forest burnt down. But what about Australia? This past fire season was lengthy and vicious, with firefighters confronting hundreds of blazes in 40+ degree heat. As the fires raged, so did debate on whether what we are witnessing today is anything outside the norm. Although bushfires have always been part of the Australian landscape, there is evidence a dramatic change is occurring.
This
alpine forest stretches for 500 kilometres across 2 states, New South Wales and Victoria. It's a complete bioregion in its own right.
The Australian Alps are our highest mountain range, home to iconic peaks like Mount Feathertop and our winter ski resorts. Most of the Alps are protected as national parks.
But what most people aren't aware is that vast areas of this bioregion are being irreversibly changed by megafires.
The irony is that these eucalypt forests actually depend on fire for their survival.
These things are just extraordinary. They produce a lot of fuel. Some people call them fuel factories, that the more you burn them, you're almost feeding the monster.
How plants co-evolve with fire fascinates forest ecologist David Bowman.
This forest here is probably one of the most fire-adapted forests on Earth. It's hard to believe that this forest was pretty well incinerated about 6 years ago. And if you look at that eucalypt there, underneath their bark is really a volcano of buds. And if you burn the trees, those buds will just erupt through the bark.
The slopes are carpeted by a mosaic of eucalypts. The high mountain ridges are dominated by alpine ash forests.
I'm surrounded by Eucalyptus delicatensis, the alpine ash. And like most eucalypts, they're born to burn. Their leaves are full of flammable oil. They surround themselves with large amounts of leaf litter that builds up as fuel. They drape themselves in bark that, when that catches alight, lofts into the air like candles and starts fires many kilometres away. And their seeds are encased in hard capsules that need fire to germinate.
But unlike its eucalypt neighbours, the alpine ash can't resprout from its trunk. Like the ponderosa pine in the US, the alpine ash is known as an obligate seeder because it can only reproduce from seed and only when the trees are mature.
The alpine ash is a really interesting tree. That's a bit like you've got a racing boat and you want to win so badly you throw away pretty well all of your safety gear. You have no lifeboats, no life rafts, no nothing. You're just going to win. It doesn't have the capacity to resprout after a fire. It's shut down all of those strategies which are typical of normal eucalypts.
Being an obligate seeder works fine, as long as the frequency of the fires remains in sync with the life cycle of the trees. Joining forces with David is National Park Manager Peter Jacobs. He's been working in the Alps since the 70s.
I guess I feel very privileged to have known these forests for many years and seen the big mature alpine ash forests.
While severe burns aren't new here, recently they've become much more frequent. Nearly all of these large alpine ash trees started life 75 years ago. They're the regrowth from Black Friday in 1939, when destructive and deadly megafires tore through 2 million hectares over just 2 January days.
To some extent we think, well, that's a thing of the past, that's an historical thing, we'd never have that again until 2003. And of course we had more than 2 million hectares burnt out, Victoria, New South Wales and the ACT. So we are certainly back in that megafire environment again.
2003 reset the clock for the alpine ash.
I think we should get some more hose. Yeah. Fire! Fire!
And for the next decade, megafires dominated Peter's work.
You can see here the big stags of the older forests that are now dead because they were killed by the fire, and this beautiful regrowth of alpine ash which has come back from those 2003 fires.
Soon after, the Great Alpine Fire of 2006 burned out 1 million hectares. And just when the Alps needed a break, lightning started another fire in 2013. So in 10 years, 3 overlapping fires struck the mountain forests, burning large areas more than once. What does that mean for the survival of alpine ash forests?
not going to become a forest giant.
Clearing tracks through the charred tangle, scientists measure the size and density of the trunks to estimate how much seed was in the trees before the burns.
210.
The good thing is that there was a lot of seed held in the canopy of the tree, and that was released by the fire, and you can see seedlings are starting to germinate from that seed.
But these trees were the lucky ones.
Or what if you suddenly come along and go boom, 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 and you give it 3 fires before it's even thinking about bearing seeds?
This is the result. Parent trees are killed. Regrowth is wiped out. The seed bank is obliterated. Even seeds in the soil are incinerated. In this national park, tall, wet forests are now a sun-scorched wasteland. We're left wearing hard hats in the bush, looking for live trees in a dead forest.
If it's a trend, then it's really amazing because we're talking about ecology in action. We're talking about climate and fire just overwriting landscape patterns.
It's only from above that you get the big picture here, and the enormity of the changes takes your breath away.
My God, look at that. You know, we're talking about an entirely different sort of landscape.
There's no chance of any regrowth of alpine ash in this area under natural conditions because the forest that was burnt had no seed on it.
Just the incredible, just smashing down of all of them. It's like matchsticks just thrown all over the place.
Nearly 90% of the Australian Alps bioregion has been burned, and 97% of the regenerating alpine ash forests have been killed.
10 years ago, did you ever use the term megafire?
No, I don't believe I did. I couldn't believe that we can have a fire these days so big in the landscape. It has really changed my way of thinking about fire, absolutely.
This may be the last we see of mature alpine ash forests in our lifetimes, perhaps forever.
It's a really amazing time, possibly a tipping point. We need to get to the bottom of, is this unprecedented? Maybe this has happened before.
It's difficult to know for sure. Neither the alpine ash of the high country nor other eucalypt species that burn more frequently contain any kind of reliable fire history.
But it's another story with the iconic trees of the southwest US. What they can tell us about the last few hundred years reveals important clues to understanding recent megafires in other parts of the world, including Australia. New Mexico's ponderosa pine is in many ways close to the eucalypt. It's highly tolerant to fire and it's used to frequent burns. But there's one key difference. The ponderosa keeps a meticulous logbook. Come rain, snow or shine, each year they lay down a distinctive ring of growth. The science of tree ring analysis, or dendrochronology, was developed around a century ago by Andrew Douglas from the University of Arizona. It's been intensively studied here in the southwest ever since. Regents Professor Tom Swetnam is a world-renowned dendrochronologist. So how old are the trees here?
Oh, these are some pretty old. They're probably 400 years old or so, maybe some 500. This is actually a good one here, it looks like. A nice big fire scar on it.
Wow,
pretty
that's
typical.
A fire scar.
Yeah, this kind of shape like this. And when I see one like this, I want to get down really close to see how many fires are recorded. And we can actually tell by looking at these ridges, these vertical ridges here.
Right, so each one of these cracks is a fire scar.
That's right, that's right. So The first fire burned here, and then the next fire come along and started again. So each one of these is a different fire. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.
So it's lived through 13 fires at least?
Yes.
Over how long?
Probably at least 300 years, maybe 400 years. These vertical ridges.
The numerous fire scars found in old living trees proves that while fire wasn't unusual here, it typically wasn't severe enough to kill the trees. And it didn't seem to bother the locals either. Long before Christopher Columbus arrived in America, it was the Pueblo Indians who called these forests home. Here, at Frijoles Canyon in Bandelier National Monument, they lived in cliff dwellings at the base of the canyon walls.
My main focus is on trying to understand how fire has varied, how it's changed through time over the last several hundred years. And now I'm increasingly interested in how people have interacted with climate and fire and forest.
Together with Dr. Craig Allen and other researchers, Tom's been investigating the Native Americans' close relationship with fire.
We've been studying fire and climate here since the 1980s.
Right.
If you take a look here, here's a reconstructed ancestral Pueblo building. And these building beams are the sort of wood material that Tom's lab has been working on.
That's right. You can see the rings on these one really distinctly. And so we've been able to match these ring patterns with tree ring chronologies from the region. We learned that these sites were mostly constructed in the early 1300s AD.
700 years ago, Pueblo Indians used blocks carved from the volcanic cliffs, held together with mud mortar and ponderosa pine, to build dwellings on the canyon floor. Up high in the canyon, they stacked rooms on top of one another, using the natural shape of the walls to support and enlarge their constructions.
These little holes in the wall aren't rooms, they're storage areas. But if you look up here, these are beam holes, and they used to create big apartments with a wall that's now eroded. So this was a room with a view.
From here, the Pueblo people would have often seen a landscape full of smoke and fire.
So what we're trying to learn is how they were able to survive here with smoke and fire in their landscape. You know, people have been moving into these landscapes in just recent decades, and we're losing homes. And firefighters trying to put fires out here have died. So we're trying to, understand how it is that we can live sustainably in these environments.
By sampling fire-scarred trees in the forests around the Pueblo ruins and correlating the dates, Tom has nailed down exactly how often local fires burned.
That is the big scar right there.
And what's changed. His base is in Tucson, Arizona, and it's the world's largest tree ring laboratory. It looks a bit like a tree from the outside. Inside, it's piled high with wood samples from all over the world. Some trees, like this giant sequoia, tell a story that goes back thousands of years.
The pine samples that we get from the Jemez Mountains, like this one, have a really distinct record of both climate and fires. So we can see the patterns. There's wide rings and narrow rings, like there's a drought year right there.
Because that's a thin line,
That's
so
right.
that's a drought.
And then there are these fire scars, and they're black lines of injuries that come right into the individual rings. And we can count them, we can see how many fires occurred, and we can date them to the year.
Tree rings show fires occurred around twice a decade in the Jemez Mountains.
In fact, the only thing more frequent than the fires are the changes of seasons.
But the most striking feature is the period where everything stops. None of the samples show fire scars in their tree rings after around 1900.
And then there'll be 100 years with no fires occurring.
On all of the trees?
Almost all of the trees.
The 1880s marks a critical transition. It was when graziers moved en masse into New Mexico. Grasslands became so degraded, they stopped the spread of surface fires. And in the early 1900s came a policy that's a key contributor to the megafires of today: fire suppression.
One careless second with a match, and America the Beautiful becomes America the Ugly. Please, help prevent forest fires.
The view of fire as an intruder, as an enemy to be stamped out, led to the virtual absence of fire for most of last century.
You know who causes little fires.
Look back thousands of years in the sediments of this region, and there's been no other period without fire. The suppression of fire over the last 120 years in New Mexico has been so unusual it's completely changed the landscape. And that's made Bill Armstrong's job today incredibly difficult. He's been fighting fires for decades, but he'd much rather light them.
You know, you cannot exclude fire from these forests. We have attempted now for 100 years, and now what we're seeing are fires that are burning with intensities and rates of spread and so forth that we can't stop. Many times when we approach these fires, it's like fighting a hurricane. It's like fighting a tornado.
What many people see as lush and healthy forest, Bill calls a tree epidemic.
See, this is the results here of our attempts at excluding fire from these forests right here. If you look around you here, you can see this is this enormous buildup of woody debris, of fuels in the ground, from trees falling over, from needles falling.
It's pretty dense here.
Yeah, we're looking at probably 800-900 trees to the acre, and this would go up like an enormous match head right now. I look at this as a verdant cancer. This is a landscape of wounds. I don't know how else to describe it. Many people would find it beautiful. I find it very sad and foreboding.
This is a firefighter's worst nightmare. Surface and ladder fuels like these logs, shrubs and small trees that help a fire move from the ground where it's relatively low intensity up to the tops of the trees where it becomes what's known as a crown fire.
Once a fire transitions into a crown fire, then there's no way that we can suppress it. It's beyond our capabilities to stop. They burn with incredible intensities and rates of spread that are faster than you and I could walk and maybe run.
In Bill's experience, there's only one way to stop this kind of a high-intensity blaze: by fighting fire with fire.
This area that we're walking through here has seen a variety of treatments over the last decade and a half. It was thinned mechanically in about 1993. It was subsequently burned.
Walking through this open woodland is like stepping back in time to the age of the Pueblo peoples. This is how their forest would have looked.
So the trees are a lot thinner here?
Yes, so it's about 600 trees to the acre when we started, and now there's about 38 trees to the acre in here.
It's clear that the major missing ingredient is ladder fuels. And this plot's very existence is a living testament to its success.
Yeah, the Cerro Grande fire in 2000, which was a very intense ground fire, burned off of the ridgetops up here with probably 150-foot flame lengths and hit this area directly with its impact. The fire dropped to the ground, came out of the crowns and burned across the surface with minimal damage to the stand as it would have done historically.
Without the same fuel load, the tree-killing crown fire instantly switched to a low-severity surface fire. And when the monstrous Las Conchas fire hit 11 years later, it was the same story.
The Las Conchas, when it burned through here, in the aftermath, you couldn't even tell that there had been a fire here as far as the trees went. The overstory vegetation, the trees, showed almost no effect at all from that fire.
And this little plot survived?
And this little plot survived. We can see what the effects would have been if historically the fires had been allowed to continue. This is what it looks like.
Bill believes that treating large areas in this way might just save forests from the sudden arrival of megafires in the southwest. But while fighting fires in the US is seen as heroic, getting the public to accept the smoke, noise and risk that comes with prescribed fire is another matter.
Let's cut to the essence. If the American public desires large, contiguous blocks of forest, if that's what they want for all the benefits that are derived from it, watershed, solitude, wildlife habitat, if that is what they want, then they have to accept fire. The choice is whether they accept it as wildfire or they can accept prescribed fire under controlled circumstances. That's the choice. The choice isn't between whether it burns or whether it doesn't.
That's a debate familiar to Australians too. Tasmanian Fire Chief Mike Brown fears that most of us are pretty blasé about the risk.
People think if they've got a capital city postcode that they're immune somehow from bushfire risk. They're not immune, and in fact there's a potential time bomb over their back fences.
And there's one Australian capital city that's more vulnerable than most. Finding out about the world of megafires is making me see my hometown of Hobart in a whole new light. Instead of forests, I'm seeing fuel. Hobart is surrounded by eucalypt bushland, backed by a towering mountain cloaked in forest.
We know that our worst fire weather comes from the northwest. That's where we get the very hot conditions, very dry winds, low humidities.
The alignment of the valleys actually funnels the hot, dry breath of severe fire weather towards the city. Fingers of flammable bushland extend into the suburbs like explosive fuses. Of all our capital cities, Hobart has one of the longest bushland boundaries, technically known as the wildland-urban interface. Where bushland meets suburb is a potential fire front. And in Greater Hobart, this boundary stretches for nearly 200 kilometres. Every fire season, this is the last line of defence. Today, the Hobart City Council is taking advantage of safe weather to treat a small part of this lengthy urban fringe. Hobart is Australia's second driest capital, in a state with a higher fuel load than the mainland due to wetter winters. Every destructive bushfire renews debate about whether enough burning off was done to prevent it. Although it's not known exactly how much strategic burning to reduce fuel happens in Tasmania before each fire season, over the last 4 years, the amount of vegetation burnt has been less than 2% of what's possible.
Fires will still impact on communities despite fuel reduction burning. So I'm an advocate for fuel reduction burning. There needs to be more of it, but we can't really see it as being the silver bullet answer to community fire protection.
For a city with as much potential fire exposure as Hobart, that's alarming, particularly when catastrophic megafires have hit the city before. One of Australia's worst disasters was Tasmania's Black Tuesday in 1967. It wasn't just one fire, but more than 100. 62 people were killed, many in Hobart, where more than 430 houses were lost in the urban area alone. The fires swept down both sides of the Derwent River. Here, it was more a city fire than a bushfire. This suburban street is just a kilometre away from the centre of Hobart City. Seems the last place you'd expect to be attacked by wildfires. But try to imagine that hot, dry, windy day in February 47 years ago when a storm of embers blasted down from the burning mountain and set this street alight. It was here that Bob Vincent's family home once stood.
I grew up here, and on the 7th of Feb, 1967, this is where it all happened. The fire came from up the top of the hill, straight down the valley here. It wasn't so much the fire front as a whole lot of sparks. The house just went up in the space of about half an hour, 3/4 an hour. It was really just come purely from embers.
With his own house fully alight, the then 20-year-old Bob feared the fire would spread.
And it came up over onto this house right over here, and I jumped up on that brick wall there, jumped over onto the roof of that house with a garden hose in my hand, lifted the ridge capping off and shoved the hose in to stop the fire that had started to ignite in underneath the ridge cap.
So your house was burning down and you're trying to save your neighbours?
Well, there was no point in trying to save our house any longer. The point was, did the fire continue on down into Sandy Bay? But this is the closest point to the city that the fire got.
While the memories of the 1967 fires remain strong, since then, the bush has grown back with more houses built in and around it.
I think we're in for another one. In fact, a 30 to 35 year cycle is about right. Well, we've now had 47 years. So I think we've got to watch out, really seriously watch out.
Inside the old Hobart Fire Station, Sandra White and her team evaluate the risks and consequences of that happening.
I used to be a ranger with Parks New South Wales, and I used to do firefighting in their remote area teams. We'd get winched into fires and operational firefighting with hand tools. We love the bush, and when we make a decision to live there, that's fine. I choose to live in that environment myself. But I need to make that choice with my eyes wide open and understand that one day I could lose my house.
To assess that possibility, both locally and statewide, her team uses computer models to light hypothetical fires. Their experiments vary the vegetation type and change the fire danger index, a combination of air temperature, relative humidity, wind speed and drought. Designed for dry forests, the Phoenix model is comparing two extremes, the worst-case scenario with no fuel reduction at all, and one where all the fuel has been burned before the fire season. So all the hazard reduction burns that people have always called for, plus more?
Plus more, everything. Every bit of fuel that we could treat, we've treated.
The model predicts the behaviour of two fires lit on a hot, windy day of very high to severe fire danger, and then left to burn.
What we do see is that the fire in the northern suburbs self-extinguishes, but the fire in the southern suburbs actually keeps going and would be impacting on houses and communities.
That's quite surprising, isn't it? You'd think if you'd remove the fuel, then you'd make the community safer from wildfire.
Yeah. There's an underlying risk that comes living in the Australian bush. And all the fuel treatment in the world, there is a residual risk that there will be fires and that those fires can create damage.
It highlights how fuel reduction alone is no silver bullet. But watch how the fires behave when there's no fuel reduction at all. Same weather conditions, same ignition times, no one trying to control them. They quickly join and burn the northern, western and southern suburbs surrounding Hobart, all the way to the coast. And this model is simulating a fire danger index of 52. In the real world, on the day of the Dunalley fire in 2013, the danger index peaked at 112. On Black Tuesday in 1967, it was 128. That's a very scary scenario, but it's not real, is it?
It's not real, no. It's a contrived scenario, and this is what we're trying to do. We're doing this modelling to try and understand where are we going to get the most benefit for our fuel treatments and what's the level or extent of fuel treatment that we need. When we say this isn't real, I guess we have seen fires burn through the back of Hobart. We saw that in 1967.
Could it be real again now?
Yes.
It's an issue for many Australian towns and cities. Urban bushfires are an ever-present danger. And one of the current limitations of this computer modelling is it doesn't factor in how climate and vegetation is likely to change over time.
Because of climate change, we're going to get changes in our vegetation type and our ecosystems That means there will be more fuel available to burn that previously wouldn't have burned. That will mean fires will become harder to suppress. Because of climate change, our fire seasons are getting longer. And so we have less time available to us to do the fuel treatments we need before it's no longer safe to do those sorts of fuel treatments.
Whether or not climate change has a hand in fires we are seeing today has been a major bone of contention. But it's a question Professor Tom Swetnam can answer. At the Tree Ring Laboratory, Tom's team has helped demonstrate that the current surge in the size and frequency of wildfires in the American West has more to do with rising temperatures than fuel load changes.
We're seeing these big fires occurring in landscapes that did not have a strong fire suppression effect. That is, for example, high elevation, northern latitude forests where surface fires are not a part of those systems. We go to trees growing at the highest elevations, really old trees growing there at the tree line, and often their growth is controlled by how warm the summer is. So warmer growing season, they have fatter rings. So we're able to actually get temperature histories from trees at the tops of the mountains.
Tree ring studies show these forests only burnt once every 100 to 300 years in the past, and that high fire years, not surprisingly, corresponded with hot, dry years. But more than half of the current increase in large fires after the mid-1980s has occurred in these northern mountain ranges and higher elevation forests. The majority of these wildfires were associated with an early snowmelt.
The snow is melting in the spring, so that by the time you come to the summer months, it's dry there and it's burning like it hasn't in hundreds of years, maybe thousands. So the mechanism is really quite evident. Warming temperatures, earlier springs, longer fire seasons, more big fires. There's no other explanation. There hasn't been a major fuels change. The sizes of the fires are extraordinary.
Compared to the previous 2 decades, large fires in the West are happening 4 times as frequently. The fire season has extended more than 2 months, and the area burned is 6.5 times larger.
The thing we can be certain of is that if you add CO2 to the atmosphere, you will warm the atmosphere, and a warmer atmosphere will be correlated with more fire activity. Yeah.
In Australia, we're also seeing vegetation types too wet to burn going up in smoke. This is Lake Macintosh, a hydroelectricity dam in the rugged beauty of Western Tasmania. It's surrounded by rainforests and tall eucalypts. Sandra White and Dave Taylor want to show me how changes in the climate can boost the impact of fires.
In 2010, a fire ripped through here and managed to cross the lake by jumping from one dead tree to another. Ignited by lightning and fed by drought, the fire burned far more than the scientists expected. The winds were so strong and the forest so dry that even the rainforest canopy started to burn. When the fire got to the other side of the lake, this is where it hit. And amazingly, it set off a crown fire in several thousand hectares of wet myrtle rainforest.
We watched it crowning and we wanted to, I guess, understand if it burnt. We haven't got a lot of records to look at fire in rainforest, particularly cool temperate rainforest.
Traditionally, these rainforests are relied on as fire breaks, wet enough to stop fires in their tracks.
When the crown fire hits a rainforest canopy, it usually decouples, and so it drops to the ground. And what we rely on in the rainforest is it'll drop to the ground and it'll hit this soggy, wet organosoil sponge, and then that's what puts the fire out.
But that didn't happen here. There was something else about the 2010 fire that continues to kill this rainforest.
This is nearly 4 years ago now, and we're still seeing more canopy loss. So it's not that we can say we've had a fire and that event is done. 4 years later, we can still come back and say, wow, this is still changing.
It wasn't just the vegetation that caught alight, the soil was burning too. And that was the end for old rainforest giants like this myrtle.
You can see there's evidence where the soil was originally up probably in this level. And because of the fire and burning the organics, now it's come down and burnt all the way down.
That's incredible. That's a subsidence of more than a metre.
And it continued to burn all the way down this level, and you can see where it's basically burnt out the root level of the tree. It's taken a couple of years to kill the tree off.
As a changing climate shifts rainfall and increases drought, the surface of the thick peaty soil dries out to form a crust that actually repels water. That means even when it does rain, the moisture doesn't penetrate and the deeper soils become drier.
And so these sponges that we could rely on to protect the rainforest actually then started to become the enemy to the rainforest because they were burning out their own root systems.
And predictions based on the old fire danger index underestimate the new risk now that this vegetation is more flammable.
Those traditional numbers at the time said this forest wouldn't burn. Did it burn? So I think now agencies are looking outside the normal box to try to take in consideration other things.
I think it's just something pretty dramatic to look at a tree that's survived for so long and then a couple of years of drought and a bad fire and then it's gone. And there's not a lot of evidence that there's any recruitment going on to replace it. So yeah, there's a sadness there.
Landscapes not meant to burn are also catching fire in other parts of the world, but on a much vaster scale. Rainforests in Borneo and in the Amazon basin, even frozen tundra in Siberia and Alaska. When they burn, they release the huge amounts of carbon they store. And here lies the great concern. So far, there's been intense focus on how climate may change fire. But with new types of plant matter burning and bigger and greater intensity fires, how will fire change the climate?
This is the question. How much of the changes going on are now driving and are going to be driving greenhouse gases emissions around the planet? And it is going to be and is already a significant effect.
So I am worried that the worst case scenario is that we get a tumbling out of control of the feedbacks between more fires, more emissions of CO2, more climate change, more hotter weather, less rain. You can go into a fire spiral, making it harder for us to pull the brakes back on.
We rely on trees to suck back the carbon dioxide from the atmosphere as they regrow. But a returning forest is no longer guaranteed.
Forests sequester about a quarter of the excess carbon that we're emitting into the atmosphere. By changing it from forest to non-forest, it's reducing the amount of carbon, CO2, that forests are able to pull out of the atmosphere.
Even without tree-killing fires, small rises in temperature are pushing many trees past their tipping point.
In the last 15 years, we've been seeing large areas of forest die from drought stress amplified by heat.
Tree mortality is still largely a mystery. This leaves big gaps in our ability to predict the future.
We don't yet know how much stress a tree can take from drought and heat before it dies. Currently, there are no climate models linked to the future of vegetation on the Earth.
In a time machine designed to push trees to their lethal limit, Dr. Nate McDowell is trying to answer these crucial questions. Here at the Los Alamos National Laboratory, his subjects swelter in heat chambers and much of their available water is siphoned off.
So what we're doing here is simulating a drought. And so what this is designed to do is remove about 45% of the snowfall and rainfall.
So basically the trees are getting drought on top of drought.
Yep, they're getting drought on top of drought. We know that it'll be 2 to 4 degrees warmer by 2050 here. But on top of that, there'll be heat waves during drought. So we've added 5 Celsius on top of the ambient temperature to simulate both.
When I step inside this chamber, I get a good idea of what a 5-degree warmer world feels like. There's temperature regulators to make sure the heat is constant, and with little water and high temperatures, it's hardly surprising this tree is suffering. In fact, this one is dying.
Tiny pores in the leaves, called stomata, allow the plant to draw in carbon dioxide for photosynthesis. But they also allow water to escape through evaporation. When it gets too hot, the stomata close shut. This protects the plant against water loss, but also stops carbon getting in.
To some extent, a plant's a plant's a plant. They share far more processes than they don't share. So if any plant is droughted and cannot eat, they will ultimately starve. There's no way around that.
By measuring changes in their stomata, energy reserves and water stress levels, Nate's team is looking at the critical stress points of trees.
Elevated temperature causes all of us, animals, mammals, and plants, to respire more, to consume our carbohydrates more. So they generally use up their fat stores or their carbohydrates, which should bring them to carbon starvation faster.
Around the lab stand stark reminders of the importance of Nate's work. Water-stressed and starved, the local ponderosas have given up the ghost, and borers have moved in.
With insects attacking as the last straw that results in their final mortality.
And warmer temperatures lead to larger outbreaks of beetles that kill more trees. In the southwest, around 20% of the forests have already been killed by the combined effects of climate and fire. As a place that's seen as a canary in the coal mine for forests of the world, it's a shocking warning for the rest of us. More disturbingly, the point at which the native forests may no longer survive has been pinpointed with high confidence by Nate's lab, using 3 separate approaches.
So we have multiple predictions that conifers will be gone from the southwest by 2050. One's from tree ring analysis, one is from model simulations, and another one is basically using the results of our experiment here and forecasting the future. And all 3 of these approaches, all of which are extremely independent from each other, say the same thing, that there should be no trees here by 2050, at least conifers.
Most of New Mexico's forests are conifers. Whether every single one is gone by 2050 or not, there's no doubt this region will be vastly different to the one I see today. And 2050 is just a few decades away.
Yeah, it'd be more like a desert, what Craig Allen refers to as weed world, which I strongly agree with. It'll be a system where there's opportunistic plants, grasses, shrubs, forbs, whatever, that can come in and take advantage of bare ground.
It's like trying to imagine the Australian Alps without the alpine ash.
If these fires are really coming as quickly as they appear to be coming, my view would be assisted landscape adaptation by moving seed stocks from different species from the lowland, which are fire resistant, and moving them up here. Very controversial view, but we've already seen the land managers have started doing controversial things.
In an unprecedented step for a national park, the fire-ravaged ash forests are getting human help to survive.
We're faced with a dilemma, is what we now do in this environment. Do we allow those natural processes to take place and just see what nature brings, or do we take the opportunity to intervene, which we can do, and reseed these areas?
Helicopters have dropped alpine ash seeds over 2,500 hectares of the triple burn forests to repair the natural cycle of renewal smashed by the alpine fires.
We'll record the plot locations. It's a 2x1 metre plot, so the corners...
It spawned a new research project that compares areas seeded by helicopter with areas of natural regeneration to see if they can simulate nature. This site was reseeded 6 months before. On his last day on the job with Parks Victoria, Peter checks for seedlings. How old would that be?
I'd suggest they're probably just a few days old.
That must be very heartening for you.
To me, this is just fantastic. There's been so much, I suppose, debate about what to do. Like we wouldn't normally intervene in a situation like that.
Although the challenge has just begun.
What we have to have happen here is for this reseeded forest to have no fire in it for at least 20 years. So it can develop seed and then it gets back to its more natural cycle again.
But even then, seeds need 6 or 7 weeks under snow to trigger their germination. As temperatures rise, the snow cover will shrink.
That scenario around climate change is really fascinating for how nature will respond, and we're living and breathing it right now.
It's strange to think they're the tallest living tree here right now.
It is amazing, isn't it? Just look at that tiny little plant there will one day be an 80-metre tall alpine ash. It's just incredible.
With luck and less fire.
Yes, and good nature.
In the politically charged debate over whether climate change or high fuel loads are responsible for severe fires, it's important to go back to basics. Fires need 3 things: oxygen, fuel and heat. By adding not 1, but 2 of these critical elements, we are stoking the furnace in an age of megafires.
I'm not sure if there is a natural fire anymore. Unless we completely take ourselves out of this landscape and do nothing, I don't believe there is a natural fire.
Wherever we live in the world, from Australia to the US, the rise of megafires is becoming a fact of life.
The ultimate fire-dependent organism are humans. We're the only species that lights them. We're the only species that fights them. And we're the only species that uses fire. Fire, we are a fire creature. Without it, we wouldn't exist. It's a gift. And how we use that gift is really what we're talking about right now.
It's almost like we've been blindly doing all of these things and forgetting about something, and it's like fire's tapping us on the shoulder and saying, hey guys, you are nothing without me. I live in your shadow. You must deal with me. Look into me and I will look into you. And it's this sort of strange reciprocal relationship which is going to answer the question, what do all these megafires mean?